It's Paul again with a short video that will teach you how to use the infamous Gram-Schmidt orthonormalization process. Traditionally, this has been despised by students because it leads to square roots when you're calculating with vectors. Dealing with square roots is even worse when you're using pencil and paper than dealing with the fractions that arise when you go to invert or row reduce a matrix. However, we've got no problems with this because we're going to do it using R, and it's actually kind of fun to do by computer. You should read the short subsection 1.7 that deals with this. In order to do this, I'm going to need dot products, which come from my vector library, and I might want to do some row reducing, so I'll load practical math. What I'm going to do is to start with a basis for a subspace and convert it into an orthonormal basis where every basis vector has unit length and any pair of basis vectors is mutually orthogonal. My subspace is going to be three-dimensional. It will consist of all the vectors in R4 that have the property that the first component plus twice the second component is equal to the third component minus twice the fourth component. Generally, the simplest way to create a subspace one-dimensional lower than Rn is to introduce a single equation like this that has to be satisfied by all the vectors. Now, to get started, I need any old basis for this subspace, and the way you make any old basis for a subspace is you begin by writing down any vector in the subspace that strikes your fancy. Here's one that's in the subspace because A2 and A4 are 0 and A1 is equal to A3. Then pick a second one, being sure not accidentally to choose a multiple of the first one. The second vector is going to work because A1 plus 2A2 and A3 minus 2A4 both have the value of 3. And for a third one, I will use the same gimmick, but I will choose 0 as my value for A1 plus 2A2 and A3 minus 4A4. So here are three vectors that lie in the subspace. We think we've constructed independent vectors, but we can check that. We bind the three vectors into a matrix, slap on a column of zeros because RREF really likes to work with square matrices, and when we do the row reduction, we discover we get three pivotal ones. We've got three independent vectors. Now we can start the Gram-Schmidt process. The first thing I have to do is take my first basis vector and convert it into a unit vector. I do that by simply dividing by the length of that vector. Notice it would be quite difficult, though not impossible, to have the components be integers at this stage. I could get 1, 0 or 0, 1. But in fact, I've got two components, each of which is equal to 1 over the square root of 2. Now what I have to do is take my second basis vector and convert it into a vector that's orthogonal to my first basis vector v1. And the way I do that is by subtracting off the component along v1. You saw this done in the second week of the course. It's w2 minus that component, which is the dot product with v1 multiplied by v1. And my check is that when I take the dot product of x with v1, I get, well, I really get 4.4 times 10 to the minus 16th, but that's good enough for me as 0. Unfortunately, x is not a unit vector, so I have to divide it by its own norm. There's my second vector, and at this point, students in a traditional course really start to hate Jorgen Peterson Gram for having invented this instrument of torture. And when I reveal that while walking through Copenhagen to a mathematical conference, he was struck and killed by a bicyclist, they all cheer for the bicyclist. But we've got nothing against Graham because this calculation is easily done in R. We just got one more basis vector to convert. Starting with W3, we subtract off the component along V1, and we also subtract off the component along V2, and we check that we've got it right, that we've made a vector X that has a zero dot product both with V1 and V2. To finish the process, we convert X to a unit vector, and the job is done. We have constructed three vectors, V1, V2, and V3, that form an orthonormal basis for this subspace. What's the easy way to check that we've succeeded? Well, let's bind these three vectors together into a matrix. This matrix A has three columns that are unit vectors. They're mutually orthogonal. You've met such matrices before. They qualify as isometries, and they have the property that when you multiply this matrix by its transpose, you get the identity matrix, and sure enough, it passes that test. Why are these orthonormal bases useful? Well, if you have an orthonormal basis and you want to find the component of a vector with respect to just a single one of these basis vectors, you can do it very easily. Starting with a vector y, which passes the test for membership in our subspace, we can construct y1, which is the component along v1, by simply evaluating the dot product with v1. Similarly, we can extract the component y2 along our second basis vector v2 and the component y3 along the third basis vector, and to prove that we've got everything right, we use these three numbers as the coefficients of v1, v2, and v3, and check that we have reconstructed, you see it down at the bottom of the screen, 4, 0, 6, 1. If we had started with a non-orthonormal basis vector, we'd have to do a lot more work. With a non-orthonormal basis, you actually have to carry out the process of row reduction. On a computer, that's perfectly easy. So I can make W1, W2, W3, and Y into a vector, ask, how do I express Y as a linear combination of those three vectors? Row reduction immediately gives us the answer. The coefficients are in the last column, and if I use AA1, 4, which is 2.5, and so on, as my three coefficients, I discover that yet again I have reconstructed the vector y. So given any basis for this subspace, we can calculate the components of a given vector relative to that basis. The advantage of an orthonormal basis is that we can do this one vector at a time. And when in a later course you get into the theory of Fourier series, you will discover that this property is extremely important. Now let's try making an orthonormal basis for R3. Here's why, as a physicist, you might want to do this. You might say, I built a piece of experimental apparatus, and when I've tested it, I've lined it up so that one axis points east, one axis points north, and one axis points up. But in my lab, I'm going to use it in an arbitrary orientation. That is, I'm going to change my three standard basis vectors into a new orthonormal basis, and I want to be sure the apparatus still works the same way. So let's construct a non-standard basis for R3. Begin with any old vector, W1, pick a second vector that's not a multiple of it for W2, and then pick as W3 anything that's not a linear combination of the first two. And just to play it safe, bind those three vectors together as the columns of a matrix, row reduce it, and make sure it row reduces to the identity matrix. Now let's do Gram-Schmidt. I've actually copied the code from above. It always works the same way. Divide W1 by its own length. to get my first unit vector. Step 2, subtract off the component of W2 along V1 to get a vector x that's orthogonal to V1, and then convert it to a unit vector. 2 down, 1 to go. Final step, start with W3, subtract off both the component of W3 along V1 and the component along V2, and you get a vector x that's guaranteed to be orthogonal both to V1 and to V2. Convert it to a unit vector, and we're done. To check that we've succeeded, we bind our 3 unit vectors into a matrix suggestively called R, and we multiply the transpose of R by R, and on getting the identity matrix, we discover we have constructed a matrix that's an isometry. Now, last week, I proved to you that cross products were preserved by rotations and multiplied by -1 when you used reflections. But we didn't really have a good way of constructing isometry matrices for any case bigger than 2 by 2. Now we've got one. We have constructed an isometry matrix. We should find out whether we've got a rotation or a reflection. That's easy. Take its determinant. It comes out to be +1. That means we're dealing with a rotation. And now we can check our cross product rule from last week. Pick any old vectors u and v. There's a couple of them. And make a new vector, uxv, by taking their cross product. Now there are 2 operations I can carry out. I could apply my rotation r directly to the cross product uxv. There's the result. Alternatively, I could first apply my isometry to u, then apply my isometry to v, and then take the cross product. I proved last week that had to give the same result, and this merely confirms that, yes, indeed, it does. It's kind of silly in some ways to generate examples of things that you've already proved, but I think when it's unfamiliar material, people, although they're happy to say, I know that's a proof, and the result has to be true, still like seeing that it works in a specific case. Now let's try with a reflection. A reflection matrix has to have a determinant of -1, and I can change the sign of the determinant by just changing the sign of one of the columns, say the second column. So this matrix F has to be a reflection matrix. I first test that it's an isometry by multiplying the transpose of F by F and getting the identity matrix, and then I check the determinant. It's -1. It's a reflection. Now let's do the cross product rule again. There's our vectors u and v. There's their cross product, and here's the result of applying F to them. 2 minus signs and a plus sign. Here's what I get if I first apply F to u, then apply F to v, then take the cross product. Same numbers, but 2 plus signs and a minus sign. I've changed the sign of the result, and that's exactly what last week's proof showed.